Now that you're familiar with the binary number system, the basic language of both computers and electronic circuits, we're ready to take a look at designing control circuits. The first step in doing that are to make truth tables and logic expressions. This is the basic procedure that we'll go through to make simple AOI logic circuits. It begins with a word problem, a situation that you want to control. The first steps in making that circuit are to create a truth table and to write a logic expression. Don't worry if these later terms don't have much meaning for you now. We'll talk about them in future activities. In this video, we're going to talk about construct a truth table, about how to write a sum of products logic expression from a truth table, about how to create a truth table given the sum of products logic expression, and about how to create a truth table when you're given a real-world problem, a set of design specs. A truth table shows how a logic design's output responds to all combinations of possible inputs. A logic design with n inputs will have 2 to the n input combinations. In other words, 2 to the n rows on this truth table. Here we have 3 inputs, x, y, z. So we have 8 rows, 8 possible combinations of inputs on our truth table. The inputs are listed in binary order on the left. The outputs are listed in the columns on the right. We have a digital count here on the inputs: 0, 1, 2, 3, 4, 5, 6, 7, a digital count in base 2. Now that you're familiar, the output column lists the output that we want to see for each combination of inputs. There's nothing magic about 3 inputs. We can have 2, 3, 4 or more inputs. We can also have multiple outputs, and we'll work later with some circuits that have more than one output for each combination of inputs. However, the inputs are always on the left, outputs are on. In order to make a logic expression from a truth table, we're going to look for each row where we have a 1 on the output column. For each of those rows, we'll write a min term that represents the combination of variables in that row. Then we'll sum those min terms together to get the SOP logic expression. Let's try an example. For this truth table, we're going to look first for the first 1 in the output column at 0, 0, 1, x naught, y naught, z is our first min term. Our next one is at x naught, y, z. Next min term, x, y naught, z naught. Next min term, x, y, z naught. We OR together, we sum together all those min terms to get our output. Remember, this SOP logic expression has 2 sides, an output as well as an input. Be sure you put the complete equation, the complete logic expression down. Okay, now you try. Write the SOP logic expression for this output F6. Stop the video, go back to the previous example if you need to, and write the logic expression on your note sheet. Then check yourself in the quiz and the answer slide that follows. You should have seen 1, 2, 3, 4, 5 min terms in the SOP logic expression. This is the unsimplified logic expression, and that's what we're working with right now. Okay, let's go the other way. How about getting a truth table if we're given a logic expression? We do that by looking at each term in the logic expression and placing a 1 in the output column for the input condition that matches that term. Some terms in the expression may match more than one input condition or more than one row on the truth table. Let's try an example. Make a truth table for this logic expression. We see we have x, y, and z, 3 input variables. So we have 2 to the 3rd, or 8 rows on our truth table. We're going to put a digital count from 0 to 7, 1 less than our total number of rows, on the input in the input columns. Okay, then we look at our first min term. X naught, y naught, z naught corresponds to a 0, 0, 0 signal. So we put a 1 in that column. XZ, however, where x is high and z is high, corresponds to 2 different rows at the bottom of our truth table. We put 1s in those columns. There are 2 different rows where x is high and z is high. There's no mention of y in this term, so we don't care what y is. X naught y z corresponds to 1 row on the truth table, a 0, 1, 1, or a digital 3. In the rows where we don't have 1s, of course, we add zeros. And our truth table is complete. Now you try. Create a truth table for this logic expression. Stop the video, go back to the previous example if you need, and make it the truth table corresponding to this logic expression on your note sheet. Then check yourself on the following quiz and answer slide. You should have seen one row that corresponded to this 1, 0, 1, 1 signal, 4 rows that corresponded to a 0, 0 signal for A and B, one row corresponding to this 1, 0, 0, 0 signal, and 2 rows that corresponded to this 1, 0, 1 signal for this truth table. Okay, now let's talk about our third possibility, making a truth table from design specs or from a real-world problem. You do that by, first of all, identifying the number of input variables. How many inputs are there that control the final output or outputs? Then you assign each of those inputs a unique variable name. You set the 0, 1 condition for each variable. In other words, you determine what does a digital 0 and a digital 1 mean in your real-world condition. Finally, you want to create your truth table. Okay, let's try. A large fuel tank has sensors that monitor temperature and pressure. Both these sensors output a logic low when they're within safety range. Alarms will sound if either sensor indicates an unsafe condition is present. Make the truth table that corresponds to this logic design. Okay, first of all, we want to look, how many input variables do we have? How many things are controlling the output? Well, there are 2 sensors, the temperature and the pressure. So we could call them T and P, logically. There's only one output, an alarm. We might call that A. Our P, pressure sensor, or 0 means safe, 1 means unsafe. Our temperature pressure T corresponds to the same set of digital variables. 0 means safe, 1 means unsafe. Finally, our alarm is going to be 0 for alarm off and 1 for alarm on. We could just as easily switch those digital conditions, but we do need to define what our digital conditions mean. Okay, we have 2 inputs, so we have 2 squared or 4 combinations of possible inputs, a digital 0, 1, 2, 3. On the right, we have our output. We want to have our alarm on if either sensor is unsafe, if either sensor is a 1. So we have, for 0, 0 signal, we want our alarm off or a 0, as we define the digital condition. For all these rows where we have at least one unsafe condition, we're going to have a 1 alarm output. And that's our truth table. Okay, now you try. Stop the video, go back to the previous example if you need to, and make the truth table corresponding to this situation on your note sheet. Then check yourself on the quiz that follows and on the answer slide. This should be your truth table. We have 3 variables now controlling our output. So we have 2 to the 3rd or 8 possible combinations of inputs. These are the situations where we want our siren to sound, where we have either the window or the door are unsecured. Now you know how to read a truth table and make sense of it, how to make a logic expression from a truth table, how to make a truth table from a logic expression, and how to make your truth table when you're given a real-world situation. We'll be doing all those 3 things in the upcoming activity. I think you're ready.